Morning, everybody, and thank you for attending today's webinar. My name is Matthew Byer, and I do technical sales at ThermTest. Today's webinar will be on cryogenic testing using the transient hot wire method, presented by our product line manager on the THW, Dr. Sophia Milona. I would just like to mention the upcoming webinars that we have coming in August and September. And if you have any questions following today's webinar, we will be conducting a short Q&A presented by Dr. Sophia Milona. You can place any questions you have in the chat box in the bottom right corner. And I will now be passing along the presentation to Dr. Sophia Milona.
Thank you, Matthew. Thank you, everybody, for attending today's webinar. My name is Sophia Milona, and today I will talk to you about the measurements of cryogenics. The agenda of today's webinar will include the definition of cryogenics and some applications. Then I will talk about the transient hot wire theory and the advantages of it. Then I will move on with the THW L1 device and the different models used during this work. I will present you the THW software and some measurements taken with our THW L1 device. And I will finish my webinar with the THW L1 sensor and some accessories coming with that. And then I would be glad to answer your questions. So the definition of cryogenics comes from the Greek word kryos, which means cold or frost, and genic, which means to produce. This definition shows that any temperature below the water freezing point, below 0 degrees Celsius, can be included. But according to NIST, cryogenics are considered all the temperatures that are below minus 180 degrees Celsius, which is the temperature above which all the common refrigerants are gases, and below which some permanent gases like nitrogen and oxygen are liquids. Also, there is the field of the high temperature cryogenics, which involves temperatures from minus 50 degrees Celsius to minus 195 degrees Celsius. The applications of the cryogenics are a lot. They can be in any industry, can be in the medicines, the biology, and the chemistry. It's as you can imagine, it can be applied in the space technology, in the cold electronics, in the food preservation industry, in the transportation and storage of gases, and in the separation of gases. According to the transient hot wire theory, the thermoconductivity of the fluid is calculated by recording the temperature rise of a thin metallic wire when this is immersed inside the fluid and the step voltage is applied to it. The wire is acting as a heating source that transfers heat from the wire to the fluid, and also as a resistance thermometer from which we can calculate the temperature rise of the fluid. Because a temperature field is around the wire, is created around the wire. This can be described from the Fourier's equation of conduction, and this can be solved as an equation of the temperature rise as a function of the logarithm of time, and from the line created, from the slope of the line that is created, we can calculate the thermoconductivity of the fluid. There are lots of advantages of the transient hot wire. It's accurate, it's convenient, it's an absolute technique, meaning that there is a full theory behind that for the measurement of the thermoconductivity of liquids. And in the case of the two-wire sensor, there is no need of calibration. And in the case of the single wire sensor, as it is our sensor, there is a need of 1-point calibration. The measurements are fast, only 1 second. There is no convection present during the measurements because of the short measuring time. The wire is heating by after applying to that a heating source, a current, and the temperature rise of the wire is monitoring by the change of the electrical resistance of the wire. The thermal conductivity of the fluid is calculated from the slope as a function of the logarithm of time, and from that we can notice that the highest the thermal conductivity, the lowest the slope, and the lowest the thermal conductivity, the highest the slope. Additionally, there is an ASTM standard that shows the thermal conductivity measurements taken with the transient hot wire technique. The THW L1 device is the one that it was used during this work. The THW L1 with the integrated platform with proprietary temperature control and high uniformity allows measurements of fluids from 10 to 200 degrees Celsius without the need of any external cooling or heating source. This temperature range can be extended from minus 150 to 300 degrees Celsius when an external cooling source is connected on the device. The THWL1 is suitable for measurements of liquids, paste, and powders with thermal conductivities from 0.1 to 2 watts per meter Kelvin. And additionally to the thermal conductivity, the thermal diffusivity, and volumetric specific heat can be measured. The fluids can have a very wide viscosity range, and the measuring time is 1 second and can be extended up to 5 seconds for fluids with very high viscosity. The repeatability of the measurements is 1% and the accuracy is 2%. And the pressure can be applied on the fluids is up to 35 bar. Also, the volume of the fluid is around 20 ml, and as I mentioned earlier, it also follows the ASTM standard for the thermal conductivity measurements using the transient hot wire technique. In this slide, you can see the specifications of the 3 models of the THWL1 device. The main differences between these 3 models is the temperature range and the pressure applied on the fluids. In the case of the basic model, the THWL1, the temperature range is from 10 to 200 degrees and the pressure can be applied is up to 20 bar, and there is no need for any external cooling apparatus. In the case of the THWL1S model, there is a need of an external cooling apparatus, and the temperature range can be extended from a minus 50 to 200 degrees. Also, in that case, the applied pressure can be up to 20 bar. The last model is the THWL1E. In that case, the temperature range can be extended from minus 150 to 300 degrees and the pressure up to 35 bar. In that case, for measurements up to minus 50 degrees, there is a need of a cooling device, a circulator that can reach these temperatures. And for measurements up to minus 50, up to 150 degrees Celsius, there is a need of a liquid nitrogen system that can be applied on connected to the THW device. The THW software, when the user opens it, can see this screen. In that case, you can notice that there is the detect power option that includes a calculation algorithm for the calculation of the power that is suitable for the thermal conductivity measurement of its fluid. This allows measurements for its fluid with a temperature rise between 2 to 4 degrees. As you can notice in this slide, from an automated schedule in the THW software, it is proposed to detect the power at each temperature step, but also the user is free to delete, add, remove, or move any step during this schedule, or make their own schedule. In that slide, you can see some measurements of ethylene glycol. When a user presses at each row, can see the temperature rise as a function of time. Additionally, they can see the temperature rise as a function of the logarithm of time. And the last graph is the deviation figure that shows it's directly connected with the quality of the measurement. As you will notice, there are quality nodes in under its measurement, and there are three different types of quality nodes. The first one is the good, that shows that the measurements are good and all the conditions are satisfied, like the temperature rise is between 2 to 4 degrees. The deviation graph is between the limits following the THW theory, and there is no disturbances during the measurement. The OK message shows that probably the user needs to apply higher power during the measurements, or there is any small noise, external noise during the measurements. The last note is the poor. That in that case, it means that the user needs either to increase or decrease the applied power in order to get the temperature rise between 2 to 4 degrees, and also check if there is any source of external vibrations on the bench where the device is located. The only exception are the conductive fluids, like the nanofluids. And if in that case the temperature rise is between 2 to 4 degrees, and there is no disturbance during the measurements, and the results are repeatable, then the user can continue with the next measurements. In that slide, you can see some measurements of different fluids in the wide thermoconductivity range and viscosity range. I prefer to show you the deviations of our measurements from the theoretical values, the literature values, in order to see which is the accuracy of the device. As you can notice, in the case of the thermal conductivity, the deviations in the whole temperature range for all the fluids is between plus minus 3%. And in the case of the thermal diffusivity and the volumetric specific heat, which are shown in the left side of this slide, the deviations of our measurements from the literature values are in between plus minus 8%. The next fluid it was measured, it was isopropanol. In that case, we decided to take measurements from 20 degrees and continue with some cooling measurements every 10 or 20 degrees. And at each temperature point, the power was detected and thermal conductivity measurements were taken. You can notice that the measurements reach up to minus 110 degrees, where we decide slowly to leave the fluid to increase the temperature. Around 100 degrees, you can see that there are some anomalous thermal conductivity measurements, and this is the area where the fluid started to melt. So in that case, there are two phases present, and you can notice the different behavior between the cooling and the melting of the isopropanol. If you notice the thermal diffusivity and the volumetric specific heat measurements, you can see that in the same temperature range, you notice the same anomalous measurements in the phase change region. The last fluid that was measured was glycerol. You can see here that it covers measurements from minus 120 to close 300 degrees. And in that case, the measurements were started with a cooling of the fluid from 20 degrees up to minus 120. And the measurements were taken every 10 degrees. Then the glycerol started to increase the temperature slowly, and you can notice again around 100 degrees there is the phase change region where the anomalous thermal conductivity measurement is detected. Probably in this range is also the glass transition state of glycerol, and the same range as before can be noticed both also in the thermal diffusivity and the volumetric specific heat measurements. Additionally, I would like to show you, because it was the only range we were able to find some literature values from 20 degrees to 260 degrees Celsius. We compare our measurements with the literature values. As you can notice, there is a 2% deviation between our measurements with the THWL1 device and with the measurements in the literature values. Here I would like to mention again that in order to take the measurements up to minus 110 degrees, a liquid nitrogen system was attached to the THWL1E device, and it was only one device that was used in order to take measurements for the whole temperature range. In order to get the measurements at the very low measurements, the very low temperature, that we need to switch sensors. As you can see in this last slide, the THWL1 sensor is made from platinum wire. The length is 40 millimeter and the diameter is 0.1 millimeter. There are two different types of sensors: the THWL1E that covers the range from minus 50 to 300 degrees, and the THWL1E LT sensor that covers the range from minus 50 to 200 degrees Celsius. Both sensors are attached in the same THWL1E device. So if you want to have the full temperature range, you will have one device, but you will need two different sensors. Additionally, there are different types of measuring cells depending on the fluids you are measuring. There is the ambient and the variable density powder cell, in case you want to measure powders by keeping the same volume. There is the observation cell, where the user can observe any changes in the fluid with the time or with the change of the temperature. And also there is the paste and PCM cell with the spring-loaded bottom lid that change the volume of the fluid. It allows to keep the continued contact of the fluid with the wire by changing the volume with the temperature, and allows accurate temperature through the whole temperature range. As I mentioned earlier, in order to cover the whole temperature range, you will need to attach a cooling system for a circulator up to minus 50 degrees Celsius and a liquid nitrogen system in the case you would like to take measurements from minus 100 or minus 150 degrees Celsius. Here I would like also to remind you again for the upcoming webinars, the one at the end of the month and the next one in September. And at this point, I would be happy to hear your questions and answer them. Thank you. If you have any questions, you can write them in the chat box. Thank you. Hello from Canada. I will wait a couple of minutes, and if you don't have any more questions for now, I will close this webinar, but also I will be happy to answer your questions if you send an email to ThermTest, or also you can find us on LinkedIn. We will be happy to answer them. Okay, I think there are some questions. Yeah. Okay, I'm happy. If you write the questions, I will be happy to answer them. An attendee says that has some questions, so I'm waiting for the questions. If anyone else thinks something, please, you can also write your questions. The first one says, the best in resolution of THW L1, THW L1S, THW L1E. They all have the same resolution. They are all using the same software. The only difference between the three models, I can go back in the slide where you can see the different models. The only differences between the three models is the temperature range and the pressure at the highest pressure that the user can apply. Other than that, they are both the same device and the same sensor, and even for the sensor, what it changes are some materials used in order to allow measurement in higher and lower temperatures. Other than that, they are the same device, the same hardware, and the same software used for all of them. I think you have another one. And yes, the quality of the measurement are the same. It's like you have the same device for all the three models. The only difference is the temperature range that you can take the measurements. It's like you have the same device with just extending temperature range and pressure. Other than that, they are all the same. Nothing changed. We don't do any discounts in the quality of the measurements. All the models are having the same quality. They are the same measurements. If you have any idea of any applications that you would like to ask, I would be happy, but it would be to answer you if you will be able to measure with the THW device. When you purchase a THW device, you get the THW software. It's not coming separated. I don't know if you have any more questions. I will be happy to answer you. I thank you for your questions. They were easy ones. But please, if you have any questions, you can send an email to info@thermtest.com or smylona@thermtest.com with any questions about applications of the THW device. And I would be very happy to answer you in any other question you have. Okay, there are some more questions. There is one question said in slope representation in the future. I'm not quite sure what you mean. If you you mean how we calculate the slope of the... So if you see here, there is a curve of the temperature rise as a function of time. Here you can get the slope, but if you get the same line as it shows here, the temperature rise as a function of the logarithm of time, you can get a straight line. From this straight line, this straight line has a slope. If you follow the THW theory, that is, and use this equation here, you can solve this equation as of the temperature rise as a function of the logarithm of time, and from the slope you will be able to calculate the thermoconductivity. It's just simple math. But if you have any questions and more details, you can send us an email in the info@thermtest.com or smylona@thermtest.com, and I will be very happy to answer your questions. Thank you very much. Have a good day. Bye.